Between June 25 and July 1, 2021, a stationary high-pressure system settled over the Pacific Northwest, producing surface temperatures 20 to 30 degrees Fahrenheit above seasonal norms across Washington, Oregon, and British Columbia. The region's infrastructure had been designed for summers where daytime highs rarely exceeded 80 degrees Fahrenheit and overnight lows dropped into the 50s. Residential buildings typically lacked air conditioning. Public cooling systems were minimal. Emergency protocols assumed heat events would last 1 to 2 days. The blocking pattern that formed in late June persisted for 6 days, trapping heat at the surface and preventing nocturnal cooling. No relief arrived. The Pacific Northwest experiences a maritime climate moderated by proximity to the Pacific Ocean and prevailing westerly winds. Average June temperatures in Seattle range from 53 degrees Fahrenheit at night to 70 degrees Fahrenheit during the day. In Portland, typical highs reach 75 degrees Fahrenheit. Infrastructure reflects these norms. Residential construction prioritizes insulation against cold and rain, with building envelopes designed to retain heat during winter months. Air conditioning penetration in the region averages below 40%, concentrated primarily in newer commercial buildings and recent residential construction. Older housing stock, which comprises the majority of units in urban cores, rarely includes mechanical cooling. Public buildings, transit systems, and healthcare facilities operate with limited cooling capacity sized for occasional warm days rather than sustained heat. Regional electrical grids are designed for winter heating demand, not extended summer air conditioning loads. Heat emergency plans in 2021 assumed short-duration events lasting 24 to 48 hours, with protocols built around the expectation that overnight temperatures would drop sufficiently to provide recovery periods. The region had no operational framework for heat persistence beyond 2 days. In mid-June 2021, an omega block formed over western North America as the jet stream retracted northward into Canada. A high-pressure ridge extended from the surface to the upper troposphere, centered over British Columbia and the Cascade Range. Subsiding air within the ridge compressed adiabatically, warming as it descended through the atmospheric column. The blocking pattern remained stationary due to a configuration of upstream troughs over the Pacific and downstream ridges over the central United States that prevented eastward progression of the system. Westerly marine air, which typically moderates coastal temperatures through onshore flow, was blocked from penetrating inland by the strength of the surface high pressure. The ridge intensified through June 24, reaching a geopotential height at 500 millibars, exceeding 594 decameters, a value occurring once per several decades in historical records for the region. Forecasting models identified the developing pattern 5 days in advance, but projected temperature maxima fell short of observed values by 5 to 10 degrees. The scale of the atmospheric blocking was larger and more persistent than climatological precedent suggested. Subsidence within the high-pressure dome compressed air columns at rates exceeding typical summer conditions, with descent occurring throughout the lower and middle troposphere. Adiabatic heating added approximately 5 to 10 degrees Celsius per kilometer of descent as air parcels were forced downward. Clear skies across the region allowed maximum solar radiation to reach the surface, with insolation values near summer solstice peak and cloud cover below 5% for 5 consecutive days. Surface heating during daylight hours was not offset by nocturnal cooling. Overnight low temperatures remained 15 to 25 degrees above normal, preventing thermal recovery in buildings and urban infrastructure. Urban heat island effects amplified temperatures in metropolitan areas, where asphalt, concrete, and building density retained daytime heat and re-radiated it after sunset. Vegetation moisture was below seasonal averages following a dry spring, reducing evaporative cooling capacity. Each successive day under the dome began with higher baseline temperatures than the previous day. By June 28th, pre-dawn temperatures in Portland exceeded the normal afternoon high. Thermal accumulation in building materials meant indoor environments lagged outdoor temperature changes by 6 to 12 hours, with peak indoor heat occurring in evening and overnight periods. On June 27th, Portland recorded 112 degrees Fahrenheit, surpassing its previous all-time high of 108 degrees Fahrenheit set in 1965, and exceeding it by 4 degrees. On June 28th, Portland reached 116 degrees Fahrenheit, breaking the record set 1 day earlier. Seattle recorded 104 degrees Fahrenheit on June 27th and 108 degrees Fahrenheit on June 28th, exceeding its prior record of 103 degrees Fahrenheit by 5 degrees. Quileute, on the Pacific Coast, where marine influence typically limits temperature extremes, reached 110 degrees Fahrenheit. Olympia recorded 110 degrees Fahrenheit. Spokane, in the interior, reached 109 degrees Fahrenheit. Lytton, British Columbia, recorded 121 degrees Fahrenheit on June 29th, the highest temperature ever measured in Canada and exceeding the previous national record by 8 degrees. Overnight lows in Seattle remained above 70 degrees Fahrenheit for 3 consecutive nights, with June 28th recording a minimum of 71 degrees Fahrenheit. Portland's low on June 28th was 75 degrees Fahrenheit, warmer than the normal daytime high. Eugene registered 111 degrees Fahrenheit. Salem reached 117 degrees Fahrenheit. Duration and magnitude combined to produce cumulative heat exposure unprecedented in modern regional records. The event was classified as exceeding a 1-in-1,000-year occurrence based on statistical climate models for the area, with some analyses suggesting the observed temperatures fell outside the expected distribution entirely. Electrical demand surged as residents without air conditioning purchased portable units from depleted retail inventory and increased fan usage to maximum capacity. Seattle City Light reported peak demand approaching winter highs, with load curves inverting from typical summer patterns. Portland General Electric recorded load increases of 15% above forecast, straining generation and transmission capacity. Grid operators issued conservation alerts requesting voluntary reduction in electricity use. Transformer failures occurred in older urban infrastructure not rated for sustained high ambient temperatures, with units in underground vaults experiencing thermal shutdown. Emergency cooling equipment in hospitals and long-term care facilities operated continuously at maximum capacity, with some HVAC systems nearing thermal limits and requiring manual monitoring. Residential air conditioning units in homes built without central cooling and relying on window or portable units struggled to maintain indoor temperatures below 85 degrees Fahrenheit, even with continuous operation. Buildings designed for passive cooling through natural ventilation and thermal mass could not achieve thermal comfort as outdoor air temperatures remained elevated through night hours. Multi-story apartment buildings without mechanical systems became heat traps, with upper floors recording indoor temperatures exceeding 95 degrees Fahrenheit. Energy consumption for cooling exceeded available capacity in localized distribution networks. Asphalt on Interstate 5 in Washington buckled near Joint Base Lewis-McChord, forcing lane closures and traffic diversion. Surface temperatures on roadways exceeded 150 degrees Fahrenheit, causing binder materials to soften and aggregate to displace. TriMet suspended light rail service in Portland after overhead electrical lines expanded beyond operational tolerances, with catenary systems sagging to unsafe clearances. Amtrak reduced Cascades route speeds to 30 miles per hour due to rail deformation risk, with inspections required every 10 miles. Seattle streetcar cables sagged below minimum clearance standards. Drawbridges in Portland experienced mechanical failures as metal components expanded, with the steel bridge requiring manual operation after automated systems malfunctioned. Airport operations were disrupted as tarmac temperatures exceeded aircraft tire and brake system ratings, forcing schedule delays. Pavement at Seattle-Tacoma International Airport required inspections for surface integrity and load-bearing capacity. Public transit vehicles without climate control became unusable during peak heat hours, with interior temperatures exceeding safe operation for drivers and passengers. Freight rail operators imposed slow orders across the region, reducing throughput by 40%. Highway departments deployed crews to apply water to bridge expansion joints to prevent structural binding. Cooling centers in Seattle, Portland, and Spokane exceeded capacity within 24 hours of opening, with facilities designed for 50 to 100 occupants receiving 200 or more. Multnomah County opened additional emergency facilities in libraries, community centers, and convention spaces. Seattle opened 14 centers across the city. Demand surpassed available space by the second day of the event. Emergency medical services reported call volumes increasing 30 to 50%, primarily for heat exhaustion, heat stroke, and cardiac events in vulnerable populations. Hospitals in the Portland metro area reached capacity in emergency departments, with ambulance diversion protocols activated at multiple facilities. Ambulance response times increased due to call volume, with some units delayed by 30 minutes or more. Fire departments conducted welfare checks on elderly and disabled residents, with crews finding individuals in distress in non-air-conditioned residences. Homeless populations lacked access to indoor cooling, with encampments reporting heat-related illness. Elderly residents in buildings without air conditioning were isolated by mobility limitations and inability to travel to cooling centers. Public messaging emphasized hydration and cooling center locations through emergency alert systems, but transportation barriers limited access for non-mobile populations. Cooling centers remained open 24 hours, exceeding initial plans for daytime-only operation. The heat dome affected approximately 10 million people across Washington, Oregon, Idaho, and British Columbia, with the majority concentrated in the I-5 corridor from Eugene to Vancouver. Continuous exposure to indoor temperatures above 85 degrees Fahrenheit persisted for 72 to 96 hours in non-air-conditioned residences, with no nocturnal relief. Oregon reported 116 heat-related deaths during the event and immediate aftermath, confirmed through medical examiner investigations. Washington confirmed 112 fatalities directly attributed to hyperthermia. British Columbia recorded 619 deaths, exceeding baseline mortality during the heat period, with the majority concentrated in the Vancouver metro area and Fraser Valley. Victims were disproportionately elderly, living alone, and residing in buildings without cooling systems. Apartment complexes with poor ventilation, single-pane windows, and western exposure recorded multiple fatalities within the same structure. Death investigations identified indoor temperatures exceeding 100 degrees Fahrenheit in residences where bodies were found, with some locations reaching 110 degrees Fahrenheit. Medical examiners documented core body temperatures at or above 106 degrees Fahrenheit in decedents. The event became the deadliest weather disaster in Pacific Northwest modern history, exceeding cumulative wildfire and flood casualties. Fatality rates were highest in census tracts with older housing stock, lower income levels, and limited tree canopy. On June 30th, the upper-level ridge began weakening as the jet stream pushed southward from its displaced position over northern Canada. Marine air from the Pacific penetrated inland on July 1 as onshore flow resumed, displacing the stagnant air mass. Temperatures in Seattle dropped to 78 degrees Fahrenheit by the afternoon of July 1. Portland recorded 82 degrees Fahrenheit, a decline of 34 degrees from the previous day's maximum. Overnight lows returned to the mid-50s across the region. The blocking pattern dissipated fully by July 2 as the ridge migrated eastward over the Rocky Mountains. Regional temperatures normalized to seasonal averages within 48 hours of pattern breakdown. Cooling centers closed as demand ceased. Emergency services returned to baseline call volumes. Infrastructure damage assessments began across transportation networks and electrical distribution systems. Power grid operators reviewed transformer and substation performance data to identify equipment failures. Transportation agencies cataloged pavement and rail damage requiring repair. Public health agencies compiled mortality data and hospitalization records. Meteorological analysis of the event began within days of its conclusion, with preliminary findings indicating the ridge's intensity and duration were outside historical variability for the region. The National Weather Service classified the event as an extreme heat dome driven by an omega blocking pattern of exceptional strength and duration. The National Oceanic and Atmospheric Administration conducted rapid attribution analysis, concluding the event's probability was increased by long-term warming trends in background climate conditions, though the specific intensity was still considered statistically rare, even within an altered baseline. The World Meteorological Organization reviewed temperature records from Lytton, British Columbia, and validated the 121 degrees Fahrenheit reading as the highest reliable temperature measurement in Canadian history. Regional governments commissioned infrastructure resilience studies to assess building stock vulnerability and cooling capacity gaps. Building code reviews examined air conditioning standards, insulation requirements, and passive cooling design for future construction. Emergency management agencies revised heat response protocols to account for multi-day events exceeding 72 hours, including provisions for overnight cooling center operation and transportation assistance. The 2021 Pacific Northwest Heat Dome was entered into meteorological records as a benchmark extreme event for mid-latitude heat under atmospheric blocking conditions, with the temperature anomalies and spatial extent used as reference parameters for climate model validation.